Welcome to this lesson on Le Chatelier's principle, one of the most important concepts in chemical equilibrium. This principle helps us understand and predict how chemical systems respond when we change their conditions. It's a powerful tool used in industrial chemistry to optimize production and in laboratories to control reactions. Throughout this video, we'll explore what this principle means and how it applies to real-world chemical processes. Le Chatelier's principle states that when a system at equilibrium experiences a stress, it will shift to counteract that stress and restore equilibrium. Think of it as nature's way of maintaining balance. A stress is any change that disturbs the equilibrium. When this happens, the system doesn't just accept the change. Instead, it reacts by shifting the position of equilibrium in a direction that opposes the disturbance. This is a fundamental behavior of all equilibrium systems, whether they're chemical reactions, physical processes, or even biological systems. There are three main types of stress that can affect a chemical equilibrium. First is concentration, which involves adding or removing reactants or products from the system. Second is temperature, which relates to heating or cooling the reaction mixture. And third is pressure, which applies specifically to reactions involving gases. Each of these stresses causes the equilibrium to shift in a predictable way, and understanding these shifts allows chemists to control reactions and maximize desired products. Let's look at how concentration changes affect equilibrium. Consider a general reaction. A plus B is in equilibrium with C plus D. If we add more reactants, meaning A or B, the system responds by shifting the equilibrium to the right. This means more products, C and D, will form to consume the added reactants. Conversely, if we add more products, the equilibrium shifts to the left, producing more reactants to counteract the increase. Removing a substance has the opposite effect. Removing reactants shifts equilibrium left, while removing products shifts it right. Temperature changes have different effects depending on whether the reaction is exothermic or endothermic. An exothermic reaction releases heat, so heat is essentially a product. When we increase the temperature of an exothermic reaction, we're adding heat, so the equilibrium shifts left toward the reactants to absorb that extra heat. On the other hand, an endothermic reaction absorbs heat, so heat acts like a reactant. Increasing temperature for an endothermic reaction shifts equilibrium to the right, toward the products, because the system uses that added heat to drive the forward reaction. Pressure changes only affect equilibrium in reactions involving gases, and the effect depends on the number of gas molecules on each side of the equation. When we increase pressure, the system responds by shifting toward the side with fewer gas molecules. This reduces the total number of gas particles and helps relieve the pressure stress. Decreasing pressure has the opposite effect. The equilibrium shifts toward the side with more gas molecules. If both sides have equal numbers of gas molecules, pressure changes have no effect on the equilibrium position. The Haber process is a perfect real-world example of Le Chatelier's principle in action. This industrial process produces ammonia from nitrogen gas and hydrogen gas. The balanced equation shows nitrogen gas plus 3 hydrogen gas molecules in equilibrium with 2 ammonia molecules plus heat. Notice there are 4 moles of gas on the left side, but only 2 moles on the right. The reaction is also exothermic, releasing heat. To maximize ammonia production, we can increase pressure, which shifts equilibrium toward the side with fewer gas molecules, the product side. We can also decrease temperature to shift the exothermic reaction toward products. These insights allow industries to produce ammonia efficiently. Let's summarize what we've learned. First, equilibrium systems naturally respond to minimize any stress applied to them. Second, changes in concentration, temperature, and pressure all trigger predictable shifts in equilibrium position. And finally, understanding these shifts is crucial for optimizing chemical processes in industry and research. Le Chatelier's principle isn't just theoretical. It's a practical tool that chemists use every day to control reactions, improve yields, and design better chemical processes. With this knowledge, you can now predict how any equilibrium system will respond to changing conditions.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.